So we already mentioned that Dalton was not completely correct in his atomic theory when he said that all atoms of a given element are identical, that they have the same mass. We understand now that there are different isotopes, and so the masses of different atoms of the same element can vary a little bit. The mass is sometimes called the atomic weight. It's the weight of an atom, or the mass of an atom. So when we talk about atomic mass, we generally are using an average, because only in special circumstances are you looking at a single isotope. Generally, you're dealing with a ginormous number of atoms, and they're going to be a mix of all the different isotopes that are naturally present. So it's an average. On the periodic table, this atomic mass is listed directly beneath each element. So the box for chlorine on the periodic table, underneath it, the Cl, it says 35.45. That's the mass of one atom of chlorine. And the unit is atomic mass units. And it's element number 17, telling us it has 17 protons in its nucleus and 17 electrons. So that's the average mass of a chlorine atom. And these are calculated according to the natural abundance of each isotope. So naturally occurring chlorine is 75.77%, chlorine 35. Those have a mass of 34.97 AMUs. 24.23% chlorine 37, mass of 36.97 AMUs. Notice that these masses are similar to the mass number. They're not exactly the same. So we can calculate the average mass. Now normally if you had like a box of, I don't know, balls or something, and you were trying to find the mass of them and the average mass, you would just weigh each of them separately, add the numbers up, and divide by the total number. That works fine if you have 10 or 20 things. But if you have, 6.022 times 10 to the 23rd atoms, you're going to spend the rest of your life adding these things up, and you're not even going to finish, right? Because it would take 14 billion years to count less than that. So what do? Well, we use something called a weighted average. So we take the percent abundance, and that's not something that you would be expected to know. It will either be provided to you, or other information in a problem will be given so that you can calculate it. We take these percent abundances and convert them to a decimal form. So we do that by just dividing by 100. So if you take the percentage and divide by 100, here's 75.77%. That's 75.77 per 100, gives us the decimal equivalent of 0.7577. We multiply that by the mass of that isotope, we get a number. We take the other isotope, chlorine 37, you take its percent abundance divided by 100, multiply by the mass of those atoms, and we get another number. And then you add those two together, and there we have the average mass of chlorine. So on the periodic table, it says 35.45 AMUs. There is no chlorine atom that has a mass of 35.45, right? But that's the average. Just like, they say the average family size is 2.1 children. Are there any families with 2.1 children? No. How can you have a tenth of a person? You can't. You either have the person or you don't, right? And yet the average, so the average can be something different than any of the individual pieces. Any questions? This is the general mathematical form, which may or may not be helpful. The atomic mass is the sum of the fraction of isotope N times the mass of isotope N. So you do that for each of the isotopes and you add them together. Another way to look at that is the fraction of isotope 1 times its mass plus the fraction of isotope 2 plus its mass times its mass plus blah, 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 blah. So let's do an example. Magnesium has 3 naturally occurring isotopes, and I don't feel like reading all those numbers. It's giving us the masses of each of them and the natural abundances, and it's asking to calculate the atomic mass of magnesium. So we're going to take the percentages, divide by 100, multiply by the individual masses, and add them together. So the first one, 78.99, so that's 0.7899, goes with the first mass listed, 23.99 AMUs. And then we've got 10%, so 10% divided by 100 is 0.1, and the next mass was 24.99 AMUs, plus the last one, 11.01%, times its mass, 25.98 AMUs. And you can just do this straight through on your calculator. So I'm getting, my calculator is telling me 24.309099 atomic mass units. What about sig figs? Pardon me? Yeah, I would go with 4 here. I am not going to grill you on sig figs on a calculation like that. You can think of this as adding, and so each of these has 2 decimal places, and so I would want to keep 2 decimal places based on that. But then I also have to consider the percentages, because sometimes, like this, in this example, they're giving us 4 sig figs, but sometimes they'll only give you 2. And that's going to limit the quality of your answer. So I would first look at number of decimal places in each of these masses, but then I'd make sure that that doesn't contradict what's given here. Each of these has 4 sig figs, and so having 4 sig figs in this final result is fine. And so we'd round this and we'd say 24.31 atomic mass units. That's the average mass of magnesium atoms. When you're doing a problem like this with a real element, you can check your work by looking at the periodic table. What's the periodic table say for magnesium? This one says 24.3051. Well, if we rounded that to 4 sig figs, it would be exactly this, 24.31. Any questions? What we like to do on an exam, so that you can't just look the answer up on a periodic table, is we'll make up an element. Because we know how things go. We were students once. Okay, so how do they measure the masses and the percent abundances of these different atoms? Atoms are too small to see. They're too small to weigh. We use a technique called mass spectrometry. And this is a technique that separates particles according to their masses. And so the results of mass spectrometry might look something like this. It's going to give you an intensity of signal and different masses. And so you'll see that there's, this is scaled to 100% for the larger one. So if this was 100% intensity for number 35, it has an atomic number of, or a mass of 35. And this has a mass of 37, and we see that this intensity is significantly less. So how does the mass spectrometer work? We actually have one just on the other side of the wall that we use with our gas chromatograph. The idea here is that you put your sample in, and we have a heat source that vaporizes the sample, puts it into the gas state. It comes through here, and there's electron beams that ionize the particles. We need to ionize them, give them a charge, so that we can make them move how we want them to move. Because if they're just neutral particles, they're just going to float around. If they're charged particles, we can accelerate them using this electrical field. So we accelerate the particles, and we shoot them through here, where they come through this magnetic field, and their trajectory is going to be bent on a basis of their mass to charge ratio. And so the heaviest particles get deflected the least, and the lightest particles get deflected the most. And so where they're hitting on the detector tells us their relative masses, and the intensity of the signal tells us how many. Yes?
How do they measure noble gases?
That's a good question. How do they measure noble gases? Well, noble gases don't like to form ions, but if you blast them with an electron beam, they will form ions. They won't stay ionized for long. They'll find something to donate their electron to or get it back from. But yeah, you can make anything an ion briefly. Good question. Any questions?